is 3. Okay. So let's start. And please give a little introduction so that context is so we know the context, especially those who were not involved in this project.
Okay. Because basically they have this kind of carbon nanotube, and experimentally they found a class of organic molecules by irradiation with UV light. This kind of molecules can decompose and deposit on the carbon nanotube surface. And this kind of functionalization will give very interesting spectroscopy features. For example, we can see the redshift of the emission of the carbon nanotube. And this is very important for telecommunication applications, I guess. So
in which spectral, I see it on the figure, but let's pronounce it, which spectral range this emitters contributing to?
this is IR.
Okay, and is it easy to just fabricate infrared emitter?
Not really.
Okay, so I think Aaron was either presenting on the group meeting and definitely writing a long introduction to one of his previous papers, how challenging is to get any infrared emitter. Okay. And before we go to the next slide, do carbon nanotubes, do pristine carbon nanotubes emit light?
Yes, they do.
In which, under which condition?
If we see the spectrum in the slide, so
Mm,
we can
I do not know how to interpret it, but I'm aware that the photoluminescence of the pristine carbon nanotubes is substantially suppressed. Maybe here they just multiplied it, or it was a big challenge to make carbon nanotube to emit. For example, one needs to isolate it from solvent by wrapping it in a polymer or biopolymer like DNA. So if it interfaces solvent, it quenches luminescence, and it was question itself. So I have a feeling that here they just multiply emission signal like 1,000 times or something like that.
I see. Okay.
So it is like threefold benefit: any infrared emitter, single photon emitter for communications, and just making carbon nanotube emit in general. Okay.
Mm-hmm.
Cool.
Cool. So basically, the class of organic molecules is kind of very simple. So basically, you have a phenol ring, and you have some small functional groups. So when the deposition happens, basically there are 6 possible binding sites. So I guess in the next slide I have a naming scheme for this kind of binding site. Can we go to the next slide temporarily?
Mm-hmm. It's a little delay. I clicked it and it makes like 3 seconds delay. Okay.
Yeah. So here I show the dopant. So dopant is just a phenol group. If we attach the phenol group to the carbon nanotube, then we have 6 possible binding sites for hydrogens. And actually, the spectroscopy features for these 6 binding sites are different. So I guess the goal is to find out what is the mechanism, what is the pathway leading to this kind of binding configurations. So can we go back to the first slide?
And before we go, I have a brief question, just to make it accessible for everyone. Um, in your binding scheme, you do have dopant and in gray, and then ortho and para in color. So why the dopant and ortho and para are different? You have one molecule binding, but why there are two spots?
Okay, so basically, for the deposition, first there is a breaking of a carbon-hydrogen bond. So by breaking, basically you have two radicals. You have a phenyl radical, you have a hydrogen radical. So here is a dopant. Excuse me. So the dopant stands for the phenyl ring, and the other colorful side stands for hydrogen.
So basically, chemical composition of each dopant is the same.
Yes.
They differ only by mutual, and since all carbon atoms on the surface of nanotube are equivalent, the placement of the phenyl ring doesn't matter. The only thing is where the hydrogen is placed. So it's mutual relative position of the phenyl and hydrogen affects spectroscopic properties.
Yes.
Okay. I went back to slide 1.
Yeah, so the left side shows the experimental emission spectrum. So the top is observed in argon, and the bottom is in the air. I guess so. Basically, in air we have lots of oxygens, and oxygen is in the triplet core state. And by comparison of these two emission spectrum, we can see the second band, which is E11 star, disappears in air. So it suggests that this kind of emission feature, maybe some transition states will interact with the triplet oxygen during the reaction. So in the right side, I just calculated the homonormal transitions using our standard method. So
would it be correct to say that this blue thing that I'm trying to highlight corresponds to this E11 star?
yes.
Okay. And what is the difference between like upper panel and lower panel?
So the upper is our original data by DFT-BBE, and the lower panel I just artificially shift by like 0.23 electron volts because PBE is not very accurate, and also there is exciton effect, which cannot be addressed by our current methodology.
And one can also convert this panel B data from electron volts into nanometers, and then plot it in the same style as experimental data, right?
Yes.
Okay.
So I guess our goal is to find out why E11 star disappears during the reaction. Okay. So to find out this strange behavior, I did some transition state search. Can I go to the next slide?
Okay.
So basically, I use the same initial configurations, and I consider 4 possible binding sites, like O+, O++, P+, and P++. So I guess
Oh, so
mention the traffic.
making
Yes.
exploring 4 possible transitions, 4 possible reactions.
Yes.
Okay.
I guess here I should mention the transition state is very, very expensive.
Mm-hmm.
Also, you need to change a lot of parameters, and also, I guess the configuration, like how atoms are arranged, really matters.
Uh-huh.
So it took me almost half a year for this kind of work.
I see. It is impressive. Yulun, there is a typed question from David. He's asking, are there ortho red and para blue? And continuation.
Yes.
Okay. And the models look to be the opposite of what is shown in the schematic. David, can you please give definition what is ortho and what is para? Like some of us here do have only physics background, so just give definition.
I'm looking at your model, and it looks like, based on how you have your schematic labeled, you have ortho and para backwards. Although I'm betting you have them backwards on the schematic, so where it says ortho, it should say para, and where it says para, it should say ortho in the schematic. So para is in your 6-membered ring, they're on the opposite sides.
Uh-huh.
So ortho is when they're on carbons that are next to each other.
Okay.
In chemistry, which appears to be how you have it done up in your models.
So the
based on your labels.
So
it looks like it's a labeling thing.
Uh-huh. But do labels look reasonable to you?
If you switch the ortho and the para, where in that area you just highlighted around, it makes sense to me. And it looks like that's how you labeled your models, is if you would switch those around.
Okay. So we just need to swap the ortho and para in here.
Yeah.
Yulun, would it be reasonable, or you want to defend what is written?
I guess I do make a mistake here.
Okay. So let me write here. So here's para, and here's ortho. David, would it does it make you happy now?
Yeah.
Okay. Yeah. Thank you. And thank you for the good eye and identifying it.
Okay. So next slide, please.
Mm-hmm.
Here, I'm just wondering if the labeling here is correct or not.
So I think it is correct. David told that when one speaks about 2 neighboring carbons, it is ortho, and I do see that on the right top panel it is two nearest carbons buckled up. So I would say that it is.
This is also class, right?
Huh?
This is also class, right?
About plus, I do not know. Maybe it is correct.
I'd have to look at your schematic to figure out plus and minuses and again.
Okay, let's go to the schematic. So plus is the one that goes parallel with the tube axis, right?
Mm-hmm.
And it is what is shown on the next slide, and it is what is here. So two middle panel top. So two nearest carbons, and they are aligned along tube axis.
Mm-hmm. Okay, so I guess the only mistake is here. It's just the scheme.
Mm-hmm.
All other places are correct. Okay, that's good.
Yeah. And next slide does show the animation. It's probably lost in transition. I do it very, very vividly on my screen, but oh, now it shows. Yep.
Okay, so basically this is just showing the trajectories for the transition state switch. So we do have a transition state about 4 electron volts, I guess.
Mm-hmm.
And here we want to figure out.
It looks more like 3 on this axis.
Okay.
Okay.
3 electron volts. Okay. So we want to figure out the spin multiplicity for this transition state.
Uh-huh.
And I did some calculations. So I guess there is a question. So basically in DFT calculations, you can control the spin multiplicity of the system. You are not sure whether each component of the system is in the same spin state, right?
So one can control only the overall multiplicity of the whole system, but there is no way,
Right.
at least I do not know the way to monitor and fix, well, probably monitor, yes, but not to determine multiplicity of individual component. This
Right.
probably would need multi-reference approach far beyond DFT.
Mm-hmm. So here we just use a trick. So basically for this transition state, we get the transition state structure of the organic molecule.
Mm-hmm.
And then we artificially replace the transition state carbon nanotube with the initial carbon nanotube and the final carbon nanotube. So the initial carbon nanotube means the pristine carbon nanotube, and the final carbon nanotube means the product. And then we compare to the energy on the different spin multiplicity. Does this make sense?
Red is singlet, blue is triplet.
Yes.
I do have, well, maybe there are more questions from group members, but I have a quick question. Just before starting thinking, typically transitions like why the middle middle stage in the lower right diagram has transition state lower than initial and final. So typically one expects transition state will be always higher in energy.
Not necessarily, because for here, the carbon nanotube geometry is different, right?
So it's not, what is shown is not the actual reaction.
That's correct.
Okay, so it is in all three situations, the geometry of the adduct of the molecule is taken in the transition state and it is the same, but the geometry of nanotube is taken at the initial point, at the transition state point, and in the final point.
Yes.
So the correct data are like the data corresponding to actual reactions are only in the middle for the transition state. For the initial and final stages of the reaction, the data are not shown.
Yes.
Okay.
So I guess my point is, for pristine carbon nanotube and for the final carbon nanotube, they will always be in the singulate bond state.
Mm-hmm. And is it important that for the transition state, singlet is lower than triplet?
Yes.
Can I once say that it is a main observation that determines the reaction, and it is like you invite all of us to follow this trend, whether in transition state singlet is lower or triplet is lower?
Yes.
Okay.
Remember in our first slide, so we see under air, the second band is disappearing, and we suspect it is due to the interaction with triplet oxygen. If the transition state is in the singulate bond state, then it is packed with triplet oxygen. Only if the transition state is in the triplet state, then it can easily react with triplet oxygen. That's why we are focusing on the spin multiplicity of a transition state here.
So if triplet would be lower, then it will be more sensitive to environment.
Yes.
Okay.
So this is the first trajectories. Let's go to the next one.
Okay.
This is for O++. Still, we can say singulate is more stable than triplet.
Okay.
Maybe go to the next one. Yeah, here this is something interesting. So for this case, we can say the triplet is more stable than the singlet. And this trajectory is corresponding to P++. I guess maybe we can go back to our first slide. We can see the spectroscopic data for P++. So I guess P++ is in the second band. This is in agreement with our expectation.
Okay. So P plus double single plus or double plus. This one, P++.
Yes.
The blue triangle.
Yes.
Okay. So according to these calculations, the reaction that leads to formation of P++ goes to transition state in the triplet and is sensitive to environment.
Yes.
Therefore, we conclude that with or without air, the reaction will go with different intensity, and with air, it will be suppressed.
Yes.
Okay. Should I go back to the slide 5?
I guess we can go to slide 6.
Okay.
Slide 6, this is for P+. And then again, for this one, we see singlet is more stable than triplet. But I guess for this feature, because experimentally they cannot observe this feature. Because I guess it is in 1.6 micron, 1.7 micron. They cannot find this peak. But if they can, we would say the intensity of this peak will remain the same on the different environment.
What is the connection to TD-SMD? So this is just a scan of possible pathways, and energy is computed either in singlet or triplet in the ground state. But on an experiment, the reaction is done by photoexciting model to overcome this barrier. So would you consider that this data for transition state search are interesting and important as a standalone calculations, or they need to be paired with TD-SMD?
To me, it is a standalone story.
Okay. So one can arrange it as a single paper, let's say, and next chapter can be done independently with only reference to this work.
I guess it depends on our strategy. If we take the lead on the project, I would definitely include TD-SMD, and also possibly the non-adiabatic coupling calculations into a single paper.
Okay.
But if you want to contribute, then this is enough, I guess.
Okay. Okay. But would you describe just how do you see connection between these results and TD-SMD calculations? Would it, for example, if one takes the initial geometry for each 4 of these transition state searches and run TD-SMD, would it go across the similar trajectory and lead to the same geometries of products, or it will or it may go in the unpredicted direction?
For TD-SMD, it's complicated because we have rapid cycles, we have the frequency of rapid cycles, we have duration, we have excitation energy, we have charge transfer character. There are too many variables.
So would it be correct to say that starting from the same initial, like in TD-SMD, one doesn't specify end point, and like in transition state search, one specifies initial and final point. Therefore, it will just find the transition state. And in TD-SMD, one doesn't specify end point. Therefore, trajectory may deviate and go into the different direction and fabricate different geometry of the product.
Yes, that's correct.
Okay. As humans, is it possible to go through to sort through several successful TD-SMD trajectories and find a pair, like TD-SMD trajectory that corresponds to a certain transition state search, at least in an approximate way? Or it is only as a good luck coincidence, and one cannot find this correspondence for each of the transition state searches?
I guess at this stage it's too early to say.
Okay. Is there anything else in this report? Okay, please join me in thanking Yulun for very interesting emergent results. And any questions are welcome from all group members. More questions one, more questions two.
Why did you use PBE functional for this study? Is the accuracy of this method enough to capture the experimental result?
So your first question is PBE functional accurate enough?
Yes.
Probably not, but I guess this is the best choice we have, because transition state is very expensive. I don't think you can use some advanced methodologies.
Other questions? Other questions one? Other questions two? Okay.
So earlier you were asking about whether, like, how to try to identify which triplet states are from your calculation. But do you think it would be possible to like use fair we and fair do to compare like the two of the triplet states in terms of total energy? So just manually fix two fair we or two up electrons, then manually fix two down electrons with fair do.
What's the point of doing that?
I guess those would be two of the possible triplet components. So I guess one's more favorable in total energy, so like it might be weighted more.
Let me interpret the question of Aaron, and I'm placing myself into the dangerous path because I can misinterpret, but let me try. In the report that has been just presented, the spin multiplicity is set up by an up-down in spin polarized calculation without specifying which part of the system is in doublet or maybe like without specifics, or just speaking as a whole thing. While if one promotes, if one rearranges orbital populations, one can specifically make either carbon nanotube triplet and keep the adduct in the singlet, or one can by specifically promoting orbitals, one can make both nanotube and adduct doublets. So one can have more mechanics and more control in the way how this specific multiplicity is composed. Aaron, was it your idea, or I started designing something different?
I think that would work too. I guess my suggestion was just manually fixing the spin state, but not necessarily atoms. I think, like earlier, we talked about that make mom command. I think with that you can specify like a magnetization for specific atom centers.
Mm-hmm.
So that might be a possible way to try to trick VASP into treating like the carbon radical. Like if you wanted to have a specific spin orientation or a specific side on the tube.
I see your point, but here, I guess for the transition state, there is some interaction between organic molecule and also the carbon nanotube. In this case, how can you separate this contribution?
Oh, so the orbitals will be a set of orbitals will mix and rearrange at each step of the reaction. Yes, I see.
Right. Even if you can identify atoms, how can you identify orbitals?
I guess it would create a new orbital, or it would have its own electronic state.
Not sure.
Okay, yeah, but thank you, Aaron, for bringing it this idea, because it correlates with active challenge in the TD-SMD trajectory that we plan to resolve for last several years. That one practices promotion between orbitals and go into the reaction, but as far as we go through the reaction, identity of orbitals change. They may intermix, and even transition between selected pair of orbitals can get different. So this is another aspect of the same problem. Let me try this countdown once again. More questions 1. More questions 2. More questions 3. Okay, let's thank Yulun once again. The formal part of the meeting is over. Everyone is welcome to disconnect, and I will stay and discuss with Amir. He did send some slides. It's okay to stay and watch them, but it is not necessary. So next week we will have presentation. How many presentations? Several presentations by. So from Yulun on the transfer of knowledge transfer on molecular dynamics and Fermi weight with spin orbit coupling. Aaron will tell how to convert molecular dynamics trajectory into couplings with spin orbit. I will just make an easy job of telling which files to transfer, and then David will do most hard part, how to convert couplings into Redfield tensor, and which input parameters to use for Redfield tensors to run for spin orbit. Okay. meeting is done. Aaron, it looks like you have some comment, no? Okay. Then formal part of the meeting is done. I'm stopping the recording and we'll share